So now what we'll do for distributed parameter line modeling is we'll take a look at some examples in PSCAD for how some of these examples I did map over into a PSCAD simulation. But before I do that, I'm going to go back and take a look at this example that I did for the lumped parameter line modeling. For what I did is I went ahead and I built a line model based on having all the detailed type of information. And so the simulation is basically just kind of a dummy simulation where I've got a source and I'm looking at the from and end sides of the line measuring voltages and current, and I have a load on the circuit in order to give me a voltage drop. But what I was using this for is to give you an example where if you were going to type in like the line construction information and that you were specifying the Bergeon model and you had a 100 ohm meter ground plane, and if you had a 10 kilometer line with 3 conductors, basically, how could you have PSCAD do these calculations for you? And so if you jump to the screen, as I showed you before, basically what you see is you see the results of the line constants program. And what you have here is you have an output, and it shows these different positive and zero sequence resistance, reactance, susceptance calculations. These are in per unit in this case, but these are basically the elements that you would use not only for doing lump parameter lines, but for distributed parameter lines as well. What's kind of interesting about this is that what this does is it prints out the series impedance matrix and the shunt admittance matrix, and these are the things you'll be taking a look at for homework assignment number 5, where I asked you to do a comparison between what you'd get using my MATLAB code versus doing these calculations in PSCAD. But you notice below this that they have what they call this modal domain data. All right, so in the theory material on 3-phase, I talked about the use of this Karen-Bauer transformation in order to convert from ABC to modal reference frame. And why am I bringing this up right here? Well, I showed you one transformation that could do that, which is the Karen-Bauer transformation. But what PSCAD does in the T-line program is it takes all this 3-phase information and kind of comes up with sort of like a custom transformation matrix. And so in this particular case, what they talk about is they talk about this modal transformation matrix. So what's interesting about this is T-line actually comes up with kind of like this customized K matrix, if you want to think about it, for this particular system. And then when you apply this K matrix to diagonalize the 3-phase coupled equations, what they actually show you is the result you get by applying that to the modal impedance matrix and the modal admittance matrix. And what you see in this case is that in the modal impedance matrix, what T-line is able to do is basically able to decouple the equations. If you look at these terms, they're primarily terms on the diagonal, where the terms on the off diagonal are very, very, very small. In this case, 0 or something on the order of 10 to minus 18. And so rather than use a Karen-Bauer transformation on a transposed line, what T-line is actually able to do is actually compute kind of like a custom transformation matrix, which does the best job as far as diagonalizing the equations. And it shows you what these modal impedances and admittances would use when you want to use the 3 modal equivalent circuits. Note what it also does in here too is it calculates the characteristic impedances for the ground and the 2 line modes. It gives you the travel times, gives you the velocities and everything. So everything that we would kind of have to do by hand, T-line actually does that, and it gives you the ability of inputting this, if you want to, directly into the line model. So anyway, I just wanted to mention that this is what's going on within this T-line program, is actually kind of computing its own kind of a customized Karen-Bauer type transformation matrix. So you don't have to go through and you know, worry about whether things are going to be transposed or not. So anyway, what we have is we've got two examples I went over for single phase. I've also got an example for three phase that I set up to show you how PSCAD would work. And what we got is we got the first example where we just simply put a surge pulse on an overhead line, and basically what we're worried about is what's happening on this 1,000-foot cable. So I'll go ahead and post these up on the Modal side as well, but for this distributed parameter case 1, I'm sorry, that's 3. For number 1, this is the equivalent circuit. And you can see what I've done is I've gone ahead and I put a source in here. In this case, what I've done is basically put in a DC source. I put in the voltage magnitude, and then I just basically set the frequency to be DC, you know, 0.001 hertz. And so it makes it kind of look like a DC source as far as doing the analysis. In this particular case, I don't have much of a impedance associated with it. So basically it's going to inject all this voltage onto the overhead line. As far as the overhead component, basically what I do is I kind of build this up from scratch. Basically you have to drag and drop the little box that corresponds to the Bergeron model. Travel time interpolation is set up as on, reflectionless line is set up as no. You have the definition canvas, and what you do on here is you put in the lengths. Now in this case, I didn't give you a length for the line. We want to make this long enough where I don't worry about any reflections from the source side. So this is just something I choose. Note it's single phase. And then this is set up for a manual entry of X, Y, and Z. So basically what I just do in this case is I load in the surge impedance of 300 ohms, and I load in the travel time in this case. It's kind of a screwy set of units right here, but that's just kind of how the input's set up. So going back to the model again, you do something kind of similar for the cable. Cable is going to be 50 ohms. So I'm setting this up for manual entry in this case. Everything else is kind of similar, but now for the 1,000 feet, I've got to translate this over to kilometers. And so I use a unit conversion for that. And then basically just put a 200 ohm resistance at the end. And then I put voltage measurements at these 3 locations on the source end at the transition point of the discontinuity and at the end of the circuit. One thing you need to do when you're running this is you need to check your time steps. So like in the project settings, these time steps have to be pretty small. And so you just make sure that you got the time steps small enough where you can properly capture everything. In this case, I've got this set up for 0.05 microseconds. So really small time step and small plotting steps as well. What this means is you're not going to run this study for a long period of time. I mean, this is something you're going to be doing in terms of probably tens of microseconds in some situations. And again, what we're really kind of interested in is just basically what's going to be the kind of like the initial transitions which occur. Okay, so just simply have one operation on the breaker where I'm going to go ahead and close this in. Pretty fast. Actually, let me take that back. It actually starts out as closed, and what I'm going to do is I'm going to keep this closed for the 10 microseconds. That's actually how I do that. So if I go back and if I take a look at the way this is modeled, basically this is a 10 microsecond pulse. So what I'm doing is I'm actually modeling the pulse effect on here by just opening and closing the switch. And so I just leave the switch initially closed and I open it up after 10 microseconds. There's a lot of different ways you can do this. There's actually sources you can use to do this, but this is just kind of a quick and dirty way of me getting this done. So really what's being applied on here is a 10 microsecond pulse. And what you could see on here, if you look on the source side of the circuit, you basically see you've got this 500 kV which is being injected, then after 10 microseconds it's going to go to 0. Now what are these other voltages that you see where the voltages are going negative and positive? Well, eventually what happens is you do get these reflections back from the discontinuity. And so you can kind of see them in the simulation, but what we're really more interested in looking at is what's going to be happening at the very beginning of the simulation, in the middle part, and also at the end. And what you could see in this case is you can see at the end, basically we've got so much of that 500 kV that gets into the cable. That gets down to the load side, we've got the reflection coefficient. And so what you can see is you can see this voltage jump up, and then we get a reflection back toward the overhead. It hits the transition between the overhead and cable. It comes back toward the load side, and we get this second transition on here. And then if you keep running this longer and longer, I mean, you could see more detail around this. But really, what we see is we actually see what this peak value is going to be, and that's really what we're kind of interested in this particular case. So I'll post this example up on the Modal site. You have a second example, which is a little bit more complicated. So this is example number 2. And as I mentioned before, this is where we would have a pre-insertion resistance in the circuit right here. And then what we're interested in is we're interested in modeling finite size overhead line and cable as well. So when we load this particular example up, then here's the circuit. You see what I'm doing in this particular case is I've got a 300 ohm impedance in the source, so that's actually being used to model the pre-insertion resistance in this particular case. As far as the source model, I'm just going to go ahead and model this as a sinusoid, and I keep the simulation time step pretty small. And so what I'm doing in this case is I'm just kind of putting a regular AC source in here. I'm just making use of the fact that it's not going to change very quickly. And then the other thing I'm doing too, since the default would be a sine waveform, is that I'm shifting this by 9 degrees so I get kind of like at the peak of the waveform. And so this is actually how it would happen in practice. And if you think about, well, what happens in microseconds, we don't move off that peak very much. And so it's almost like we're putting in a DC value in a way. This just gives us a little bit more accuracy, I guess. So then anyway, as far as the overhead model, this is kind of similar to what we did before, where if you use the Bergeron model, then we can go ahead and we can enter in the surge impedance. We can also have the travel time loaded in here. Do the same for the cable. I got a load on at the ending side, and the thing that's different in this particular case is I'm looking at a lot more complicated reflections. But since I got 300 ohms at the source and I've got a 300 ohm cable, I'm not going to be getting any reflections from the source end of the circuit going back toward the lines. And so you can go ahead and you can run this. I just ask you to do this for 3 microseconds. It takes a little while to crank out the results in this case. And you can see that this is going to be comparable with what we got like doing the by hand analysis. And so if you're looking at what's going on at bus number 3, basically you have the time delay it takes for the surge to travel down the overhead and the cable. And then basically what happens is when you look at the reflection coefficient at the end of the cable, then you can kind of figure out what this first peak's going to be, and you could also get into more detail about what's happening at the uh, the middle point as well in the circuit. So anyway, this would just kind of give you an ability to kind of check the work you've done by hand, or if then later on, if you want to do um, some system analysis using PSCAD, just kind of give you some examples for how you can set up the circuit modeling. Now, there's not a lot of instances in power systems where we would be doing single phase. A lot of the cases we would be running would actually be more like three phase, so we have to have this ability of running three phase cases as well. And so in the notes, there's also a third example. Yeah, example number 3, where we've got a circuit and we've got a section 1 and section 2. The first section is 1,000 miles, the second section is only 5.78 miles. Again, the reason why I chose such a large distance for section 1 is it didn't want you to have to worry about any reflections coming back from the source side of the circuit. In this particular scenario, what we're doing is we're modeling a lightning strike, and we'll talk about that subject in the next lecture about what lightning would look like as far as a modeling standpoint. But what lightning is being represented as in this case right here is being represented as a current injection. So basically, if you think about a bolt of lightning striking a point, basically what that's going to look like, it's going to look like a current injection. And what happens is the current ramps up at a very high rate, and then it tails off. And so in this example right here, I'm showing it ramping up 20 microseconds and ramping back all the way back down at 50 microseconds. We'll talk more about what are some typical numbers for lightning strikes. And a lot of these examples, I'm choosing kind of like round numbers and make these easier to work by hand. But you want to model a lightning strike on phase C, and we want to see what the impact's going to be at the load. And so this load is a Y-connected 250 ohm load. And so what you're given in this case is you're given all these different inductances. You're given L1 and L0 and C1 and C0. And what you could do is for each section, you can use 1 over the square root of LC to get the velocity of propagation, and you use the square root of L over C to get the surge impedance. And you'll have a different surge impedance for the ground mode than you'll have for the line modes. Okay, so anyway, we want to set this up in using PSCAD. All right, so the way this looks in PSCAD, and you'll see how this is different than three-phase, is I've got the line model set up, but there's another element you could use in PSCAD, which is basically kind of like a splitter. So you have an element that's made to be put at the end of transmission lines, and what this does is it splits this into the individual three phase where you can access each phase. Because this overhead line model, it's one way of doing that would be just to draw that as a three-phase element where the connection is by default three-phase. But let's suppose you want to put a fault on a single phase, or you want to put a current injection on a single phase. Well, what you need to do is you need to use this transmission line splitting module. And so what you do is you would put this at the end of the line section. You would basically break out phases A, B, and C. And then once this is broken out, then you'd convert back to the three-phase connection model. And then you would finish out the rest of that overhead segment. So some of that overhead impedance is on the left, some of this impedance is on the right. And then when you get to the cable, I don't think you necessarily need to split this out. I mean, I just did this to give me a little bit more flexibility in the model. And then when I got to the load end, I split it up as well, so you can just see that we have a Y-connected load. So sometimes I just split things up in a way just so you can kind of see what's going on and there's no ambiguity for how this is being interpreted by PSCAD. So what is the source in the circuit? Well, the source in the circuit is a current injection. And this is being modeled as a controlled current source. And so what you would have is you'd have this controlled current source. And what you're going to be doing in this case is you're going to be controlling this through this other element, which is a surge generator. What you can do is you can enter in the characteristics of this. So you can enter in the peak value, you can enter in what's the rise time, you can enter in what's the decay time. And then this basically takes this function and drives it into the current generator, and then basically it just kind of converts this into the ampere current injection. And then if you want to plot this out, then you can create, this little plotting channel called surge. And so what I'm doing in this case is I got measurements at various points on the circuit right here, but on the load what I'm doing is I'm putting all 3 phases on here so I could see what's going on. And what you would think is going to happen if this is being injected into phase C, I should see most of my change in the voltage on phase C, but because of the mutual coupling, I should see something on the adjacent phases as well. So what I'm doing in this case is I'm mostly focusing on what's going on at the load, but I'm just plotting the surge, just make sure I've got the data loaded in correctly. And when I type in run on this, then I can go ahead and run the simulation. Again, it takes a little while to run. And basically what I see on the impacted phase, that I get this really huge voltage. And this is jumping up to about a megavolt. All right, so what's happening in this case, if I'm injecting this current, maybe this current doesn't seem like that high value, but then you have to multiply that by the surge impedance to get the voltage. And so what's happening in this case is that current injection translates into a really high voltage. Then basically what we have is we have this triangular waveform that's propagating down the line. What you see on the adjacent phases is you see the impact of mutual coupling. And what's kind of interesting is on the adjacent phases, this is going to go negative and then it goes positive because of the way the mutual coupling works. And what we're interested in looking at as far as the stress is how high and how fast this voltage on the folded phase changes. Because if this voltage becomes too high or the rate of change is too high, then what we can actually see is we could see some damage to the load, or maybe before it even gets to the load, when it hits the cable, this voltage could be such that we cause too much stress on the cable, and then it might actually cause some damage to the cable. When we have the overhead lines and we have this really high voltage on here, as we'll talk about later on when we talk about insulation, that could actually flash over, and all we need to do is just clear that fault that's caused by the flashover. But if a large surge hits the cable, then that'll cause a failure of the insulation, which is going to become a permanent failure. So we'll get into that later on, but this just is kind of like some preliminary things you need to have in order to do like lightning strike analysis and then later on to look at insulation coordination. The modeling of these overheads and these cables for 3-phase is kind of similar to what we were doing before. The only thing that's really different in this case is you would need to enter in the positive sequence values for the surge impedance for, I guess you can call it the line modes, which is they call it the positive sequence impedance here, and for the ground modes, which they refer to as the zero sequence impedance. And you're going to have the different speeds. And as we talked about, the speed of propagation for the ground mode is typically going to be different than that for the line mode. And then in this case right here, we're also putting some resistance value. You could put some resistance values in there if you have them. In this case, we were assuming lossless models, and so we didn't put any resistance in there. But if you wanted to model the loss effect and what would happen because of the resistance in the line, then you could also put in positive sequence and zero sequence values. And I think I have to have a minimum value in here just for convergence sake. So anyway, you'll be taking a look at this a little bit later on in your project, because the project's going to involve doing some three-phase fault analysis. But basically, this is the Bergeron model again, and they say really the only difference between doing the three-phase modeling and the single-phase modeling is for the three-phase modeling, you need to have these positive and zero sequence values loaded in, either for L, C, and R, or for the surge impedances and the traveling times. And then the other thing that would be a little bit different than a lot of your events, if they're single phase, is going to require to use some of these breakout connections where you can apply some single phase events in this case.